So in this lesson, we're continuing our work on probability distributions of continuous variables, and we want to be able to use the frequency distribution of a continuous random variable to compute probabilities. So this kind of is an extension of what we had done with discrete probability distributions and our work in A and B with continuous variables. So let's just jump in by taking a look at an example here with some data. The growing season is the number of days from the last frost in the spring until the first frost in the fall. The growing season for some areas in Ontario are listed below, over here on sort of the right of your page. So these are in days. So they took a bunch of regions, measured how long the growing season was, and just recorded all the numbers here. Let's say we have a probability question that we're being asked here. Find the probability that the growing season will be 162 days, or 164 days, or 163 days, or 220 days. So we want the probability that this variable is going to take on some value. Up until now, we have been thinking about questions like this by saying, okay, the probability of this event is the number of times this event occurs divided by the number of things in our sample space. And if we look at our sample space, we might take each one of these numbers here as our sample space and say, okay, there are 57 things in our sample space. So if we want to figure out the probability that the growing season is 162 days, we just need to see how many times that occurs in our sample space. So we would go through all of our data and we would say, aha, 162 is right there. And that is the only time that it comes out, that it occurs. So the probability that our growing season is going to be 162 days is 1 over 57. Now, let's repeat this for 164 days. Again, we want to go through and we want to see how many times 164 appears. It appears down here. Appears again over here, so that looks like it's 2 ways. So that would be 2 over 57. And we say, okay, well, we've done 162, we've done 164. Let's do 163 days. So let's see, we scan through our list. And we scan through it again. We keep scanning, we keep scanning, and we find out that 163 does not occur anywhere on our list. So we would say, okay, our probability is 0 out of 57. Then we would say, okay, probability of 220 days. We go through our list, and we find that 220, again, occurs twice. Here and here. So the probability that this would be, that the growing season would be 220 days is 2 out of 57. So we might take these numbers that we've calculated here, turn them into percents, and then we're going to think about whether these make sense. So 162 days, we get 1.8%. 163 days, we get 0%. 164 days, 3.5%. And 220, 3.5%. Does this make sense? Well, I've taken the data here and I've put it together into a histogram. Okay? And when we look at this histogram, we see that the peak of our distribution here is between 160 and 170 days. So looking at this, we would think to ourselves, okay, this is the most likely length for a growing season. This is where the peak of the distribution is. This is where numbers are most likely to fall. So it's more likely that we get a growing season between 160 and 170 days. Whereas if we're looking at, say, 120 days or something like 220 days, it doesn't look like it's all that likely. Okay? The frequency is much lower, so the probability is going to be much, much lower. But if we look at these specific numbers here, they don't seem to reflect that. This suggests that we have about a 2% chance of getting 162 days, about a 4% chance of getting 164 days. So these two have a probability, but absolutely 0 chance of getting something in between them. which doesn't seem to make any sense either. You would think that the probability for 163 days would be very similar to the probability of 164 days. Okay? And based on the histogram, you would think that the probability for 220 days would be considerably lower than the probability of something that is between 160 and 170. But this tells us that the probability is exactly the same. So what the heck is going on here? And the problem, I'm going to sort of answer my own question here and say that this doesn't really make sense. Okay? And part of the problem is that we're asking the question wrong. I have been treating this growing season as a discrete variable. And I really want to think of it as a continuous variable. So if we want to think about it as a continuous variable, we're going to ask questions not about specific values, but about ranges of values. So just like when we were graphing our frequency distribution for a discrete variable versus a continuous variable, when we were doing a discrete variable, we had the number of times something would turn up. And we had a little bar representing the number of times 5 showed up when we rolled our die. But when we're working with continuous variables, we are graphing the number of times something falls within a certain range. We look at a range from 130 to 140 and say how many times has something fallen in that range. So we have to think about it the same way when we're doing probabilities. So a better question to ask, and here I've given the frequency distribution here, what is the probability that the growing season is between 160 and 170 days? So I'm asking about a range of values rather than a specific value that is inside that range. So if we want the probability that our continuous variable x is between 170 and 160, and I've put the equal sign here with 170 because when I did this frequency distribution, I included the value 170 on the end of the range. Okay? We can just look at our frequency distribution here. The frequency at this point is 9. Okay? There are 9 things in that range out of a total possible number of 57 things. So 9 out of 57, or about 15.8%. Now, I was able to answer this question that it was between 160 and 170 days because I'm asking about a range of 10 days here. Because when I made my frequency distribution, I made my bin width or my bucket size to be 10 days. Okay. So sort of the distribution that we use to answer it and the questions that we can ask about the distribution sort of have to match up a little bit. So what is the probability that the growing season is going to be longer than 200 days? So to write that in terms of probability that our variable x is going to be greater than 200 is going to be, well, we look at our frequency distribution and we look for all of the ranges that have data which is greater than 200 days. So that's going to be everything from here to the end. Okay. So we can total these all up. 7 plus 6 plus 1 gives us 14. So we can just 7 plus 6 plus 1 out of a total possible number of 57 again. So we get 14 out of 57, which is about 24.6%. Now, when we're comparing probabilities that we get, we have to be a little bit careful that we are comparing, that we're sort of comparing apples to apples and not apples to oranges. So if we were to compare this probability here to this one here, we might say, oh, this probability is much larger. It's 24% rather than about 16%. But the range that this encompasses here is a much larger range than what we have here. This range goes from 200 all the way up to, well, 240, 250. Okay, so we have to just be careful, mindful of that when we're comparing these probabilities. Okay. So let's do a question where we are actually comparing probabilities here. Which is more likely, a growing season of 63 days or a growing season of 138 days? Okay. And to answer this question, we're going to use this histogram that I've made here using the same data. Notice that I've changed the bin width here, or the bucket size. Okay, so I've decreased it down to 5 days. So that changes what the histogram looks like. Our other histogram here has a very nice, a little bit smoother distribution here with a pronounced peak in the middle. This one here is a little bit more jagged, but we can still use it to do a probability question here. So if we're interested in the probability of the growing season being 163 days, what we really have to ask about is how likely is it that the growing season is going to fall into a range of values around 163. And if we look at our histogram here, the range that corresponds to a value of 163 would be 160 to 165. So for the probability of 163 days, we're really going to calculate the probability that our variable is less than 165 and greater than 160. And working on the histogram here, we can see that there's 1, 2, 3, 4, 5 out of, again, 57 things in our sample space. So the probability of a growing season between 160 and 165 is approximately, let's see, 8.8%. For 138 days, the range that we're interested in is going to be from 135 to 140. So the probability that our growing season is between 140 and 135 is going to be 1, 2, 3, 3 out of 57, or approximately 5.3%. So because these were probabilities of the same ranges here, we got a range of 5 in each case, there's no issues when we compare them. So we can simply say that because the probability that the growing season, or the length of the growing season, is going to fall into this range rather than this range, it's more likely that there's going to be a growing season of 163 rather than a growing season of 138. So a growing season of 163 is more likely. And that's where we'll stop.